the screen and let the next group, which is the last group for the ME presentation today, to load up their slides. And so this is a fourth project this morning and the last one from the mechanical engineering capstone for this year. So this project is titled Design, Manufacturing, and Characterization of Additively Manufactured Lattice Structure for the NASA Human Exploration Rover Challenge. And this is supervised by myself, Dr. Klein, and Dr. Tyagi, and sponsored by the NASA grant. So a little background or history about this NASA Human Exploration Rover Challenge at UDC. So this is 30 year we have been participating in this challenge. So we have designed 3 rovers so far. Each year we go to Alabama, Huntsville, Alabama, where the Marshall Space Flight Center is located, to compete with around 100 national and international teams annually for this competition. And the team has been, the rover team at UDC has been doing extremely well for the past few years. They design and build the human-powered rover, during their spare time, and to compete with other teams, and everything from scratch. They have to design, build, and test. So this project is to look at how we can utilize advanced manufacturing technique to produce this lattice structure, which is found to have similar mechanical strength but greatly reduced weight. So we were, because weight is one of the critical design consideration in the rover, so the team is trying to utilize this technique as a special structure to modify some of the parts they use in their rover design to reduce the weight while maintaining the mechanical strength they need. So with that, I will turn over to the team and have them present their project. And again, please hold your question to the end, but feel free to type in the chat box anytime. And also don't forget, fill out the survey form and select the right project when you do that. And so are you ready, Giancarlo?
Yeah, I think we're all set.
Okay, you can start anytime.
Okay, so our project is, as Dr. Shu introduced, the design, manufacturing, and characterization of additively manufactured lattice structures for the NASA Human Exploration Rover Challenge. I'm Giancarlo, and I'm joined here by James and Waleed, and you can see some of our product that we made using these design principles. So just to give you a brief outline as to what we're going to be doing. So we'll explain a little bit about what the NASA Human Exploration Rover Challenge is and the design problem around that. Some of our lattice structure research, the design and analysis of these structures, fabrication, mechanical testing, post-processing, the conclusions we've drawn from that work, and future work and acknowledgements. So just to give a little bit of background, the NASA Human Exploration Rover Challenge is a NASA competition which takes place in Huntsville, Alabama. It's an international competition involving approximately 100 participants, 50 high schools and 50 universities. And participating teams must develop a human-powered rover which can navigate a course of simulated lunar and Martian terrain and complete various challenges. The teams are competing for points, so they are competing on the basis of completion time as well as challenges completed. And really the main takeaway is this rewards a robust design that can complete the course in the allotted time. So it encourages the teams to think about the development of technology and design thinking for aerospace applications. Unfortunately, as with everything, the 2020 challenge was canceled due to the pandemic, but we still got a fair amount of work done. So as the rover is being built, weight is a major concern. The more weight we add to the rover is just incurring a penalty because the rider is producing the same amount of power when they're pedaling. So parts of the rover, such as, for instance, the steering knuckles, have to be very precisely manufactured, but they're also used multiple times on the rover, up to 4 times. So if we reduce the steering knuckle by a pound, we actually get a 4-pound reduction in overall weight, which doesn't sound like a lot, but it really starts adding up when you have, say, a 195-pound rover or a 150-pound rover. Um, so we took on the development of a new knuckle design with emphasis on light. Could you please mute, please? Thanks. Uh, we worked on development of a new knuckle design with emphasis on lightweight and high strength. So looking at some solutions for this, metal foams and honeycombs and offer substantial benefits. So they have a high specific strength, but they are hard to manufacture, expensive, and you have to bond them to your parts either with adhesives, welding, or another process. So that is a failure mode. The additively manufactured metals that we can produce here in school, though, can incorporate lightweight lattice structures within a shelled solid all in one piece. So we can see up to a 50% weight reduction without a large reduction in strength of the part. So these lattice structures are defined by a repeating unit cell structure, which you can either have fill a void or outright replace a solid. These hold great promise for aerospace applications. So again, the high specific strength is a huge benefit, where weight is a major concern. Thermal isolation, so they're relatively small contact area due to the size of the lattice. And they can be used in heat exchange applications as well. But obviously these can't be created through traditional manufacturing. There's a lot of complex curves and angles. So really the way to make these is through an additive process. So to that end, we're using a 3D metal printer, and that gives us some constraints. So there's volumetric constraint for one. The build platform is 250 by 250 by 325 millimeters in size. And the powder is quite expensive, so there's a cost associated with each part volume. So we want to minimize our building size as much as possible. There's a Z height constraint, so the amount of powder on hand limits the amount of build height that we have. So we have a little bit less than 100 millimeters total build height. And the printer itself is filled with the raging steel powder. It's easy to work with, print, and process, and it has really great mechanical properties, which we'll go into in a little bit more detail. So this is a steering knuckle design. So we did weight reduction of the parts with simulation of the shell without the lattice structure. We found about 1.56 micron displacement with 1.8 kilonewtons of force on the knuckle. So the shelled area you see there is going to be filled with the lattice structure, and that was determined through our experimental testing of the lattices. I'm going to hand you off to James. We'll go into more detail on the lattice.
Thanks, John. So in order to create these lattice structures and implement them into our design, we used Creo 6.0, which is actually the school's preferred 3D modeling system. We actually found that their lattice structuring module was one of the more robust, which was great for us. So it was broken down in a few sections. The beams type structures, which were sort of the first push lattice structures, the 2.5D, which are great for uniaxial strength, and then the formula driven, which is a new set of lattice structures that have been introduced in Creo 6.0. And so with our research, we looked into what data we could find about these lattice structures. So we actually found a really excellent article where a team had tested these pretend lattice structures with miraging steel using the EOSint M280 3D printer, which is what we'll be using. So it was a great direction for us to take our project. So it gave us stress strain curves for each structure. And then it gave the peak stress, plateau stress, toughness, and Young's modulus. So we looked at the data that we were given. We get a comparison graph here of the peak stress for relative densities of each of the different structures that they tested. We can see here we've highlighted the sheet diamond and the relative density of 10%. It's head and shoulders over the other structures, and then at 25%, it's not quite as greatly over the other structures, but it's still significantly better. So we did a decision matrix to decide which structure we wanted to use in order to move forward in our project. So we took a couple of criteria based on what we had: is plateau stress, Young's modulus, toughness, ultimate strength, and of course the availability of the lattice structure within the program we were using. So a few of them that were kind of stronger we weren't able to use, but again, the sheet diamond in terms of across the board strengths and availability we were able to use. So that Next slide, yeah. And then so that sort of changed the scope of our project a little bit. We originally were going to use different lattice structures and test them out, but we actually decided we were going to go with different densities of the sheet diamond structure, since we found it to be much greater in our research than the other structures. You can see here we've got the equation for the sheet diamond structure, a lot of cosine and sine waves, so a very curved structure. And then, so what we decided to use is a data trend based on densities and strength characteristics to decide which density we would use for the final rover print. So here is a stress strain curve for differing densities for the sheet diamond structure at 25%, 20%, and 16%. You can see that for each, it's about a 5% jump for each density. You get about a 25% gain in the peak stress, and about the same in the strain area as well. So you get a lot of gain even from even earlier. We saw it between 10 and 25%. We saw a lot of strength gain. We still get it in between these different nominal notches. So we attempted to do some structural analysis. So you can see in the top left corner, it's a simplified rep of the lattice structure where we had tried to do shells on each side in order to apply physics loads onto the structure. We found a lot of trouble with it, though. The structure itself, even when you try to transfer it from PTC Creo parametric to simulate, the lattice structure doesn't propagate. So we found a few ways to get around that by transferring it to an STL file, back to into a step file, and then back into programs like ANSYS. And then you can see here on the bottom left is a mesh that we were able to get out of ANSYS, which is not really defining the shape of what we're looking at, because it's not including all of the empty space between the lattice. And that was the best we were able to come up with. We actually found out that many research organizations are just doing experimental data because simulation is so complex. I think with our program, we were able to do up to like 10,000 facets, and this structure had over 600,000 facets. So it was just a little too high for us, and we had too many struggles with importing. So the equipment used, we used our school supplied EOSint M280 direct metal laser sintering printer. So it's a powder-based printer with a 400-watt laser, particle sizes of 50 to 60 microns. So was a grant that we got the machine at the school, so we got it up and running with some MS1 raging steel this year, which is a great, like, high strength, large, low carbon steel used in aerospace applications. And we use the MS1 powder that's made specifically for EOS by the EOS for the US printer. So the materials that we needed in order, you can see a little video here of the process of the powder bed, the scraper pushing the powder across the bed, and then the laser sintering the structures together. Pretty interesting. So the supplies we needed were the maraging steel powder. We needed a maraging steel build plates, and then nitrogen gas as the shield gas in order to do the printing. The other requirements were chem polishing, different acids, nitric, phosphoric, and hydrochloric, provided by Dr. Tyaghi's nanotechnology lab. So here are just some quick properties of the MS1 as printed. Not going to go through them too much, but we can see at a gigapascal or greater in tensile strength, and same with yield strength, that this is a very strong material. So printing and testing. So the initial samples were printed with a carbon fiber brush blade. So there's 3 different blades you can potentially use for the system: a ceramic blade, a carbon fiber blade, and a high-speed steel blade. So we had to go with the carbon fiber brush blade because it's the best for high quality or complex prints as well. Issues with using ceramic blade, which can potentially hit the we potentially hit the structure and break it, and then with the high speed steel and the MS1 is going to be magnetic, so potential for the beads just attaching to the blade. So we made compressive test samples. An example of ASTM E9. We use misprinted tensile specimen samples for 3-point beam loading, and then as well we have printed more tensile tests for ASTM E8 standards, and in the XY direction, and we'd like to test those. And I'll pass it off to Waleed.
Thank you. So shown in both figures is our printed specimen that we printed to perform our mechanical testing on. The left sample is the dog bone shaped specimen with the lattice structure that we printed for tensile testing. And on the right sample here is the cylinder shaped specimen with lattice structure as well that we printed for our compression testing. The table shown here represents different types of densities for our printed samples. We have 3 different types of densities: 30%, 40%, and 50% that we tested. And this is to help support the purpose of our project in terms of weight reduction, while also maintaining our strength properties. So we have here the 30% relative density sample carries a weight of 5.3 grams. The 40% sample carries a weight of 6.4 grams, and the 50% shares a weight of 8 grams. Shown here, the 30% actual weight was off from expected weight after printed, and this is due to excessive residual powder stuck on the part. And we also turned the parts on the lathe, so we might have removed uneven supported structures. So off to mechanical testing. So understanding our printed samples, mechanical properties, compression test, bending test, and tensile test are the tests we prepared our printed specimen for, and to roughly follow the American Society for Testing and Material Standards. So unfortunately, because of our lattice structure printed design, the test pieces are not solid per these ASTM testing guidelines. And shown on the top figure is the mechanical testing machine that we used, and it is called the Admit Expert 2600. It is located on campus in Building 42. The bottom figure shows the setup of our compression test. As you can see, our compression specimen is installed under the inline fixture. Although this fixture here is for bending fixture, and a platinum fixture would be more recommended for this compression test. But we used the tools that were available at the time to minimize delays and costs. Plans to conduct the tensile testing, but due to the spring pandemic, it was the work for it was paused. So the next slide here is the compression test and a video. And we had seven specimens in total for our compression, 3 in 30%, 2 in 40%, and 2 in 50%. The test speed was run at 5 millimeters per minute, and the force range was set to 20 kilonewtons. So the result is a linear graph representing our best curves from all samples. And we have the stress versus strain comparing the different types of 3 densities. The table on the right is viewing the the peak stresses that each density could withhold during the compression test. So we look at the graph, we are looking at the highest point before the line starts to fall and decrease. Where the here we have the 30% relative density falls at 158 megapascals, 40% at 211 megapascals, and the 50% at 188 megapascals. These results appear to be inconsistent with expected, due to the 40% appears significantly stronger than the 50%, and this demonstrates to the team that need for additional testing, as flaws may be due to printing or lack of post-processing. So this next test is our 3-point bending test, and we have 3 specimens of each.
I apologize, it seems like PowerPoint crashed. Let me reopen.
Thank you. So again, we had 3 specimens of each. We had the 30% relative density and 40% relative density, but unfortunately the 50% relative density were lost due to technical difficulties with the machine. So the samples were mostly the same, with only one of 30% samples showing a major defect that reduced the flexural strength of the specimen. The data shows the flexural strength is 168 megapascals for 30% density and 248 megapascals for 40% density. This shows us an increase of about 40% in flexural strength, even without the third point from the 50%. And the yield strength here shows that it's for the 30% brewing, it being 110 megapascals, and for the 40%, it equals 133 megapascals. So again here, we are just comparing the 2 different densities. This time we're adding information on the solid density, the data from the manufacturer specs on the material that we shared in the previous slide from mechanical properties, sorry. And due to no available flexural data, we are making comparison to the manufacturer's specifications for tensile properties for as printed parts. Although we cannot confirm the properties are the same, we cannot assume the specimen failed in tension from the flexural test for data comparison. So our main takeaway from this is that the lattice structure generally underperformed compared to as printed solid parts specifications in result to bending. And I would like to pass the next to my colleague Giancarlo.
Okay, thank you, Waleed. So I'm going to go a little bit over some of the post-processing, the work that we've done on the pieces here. So all of these printed pieces have some unwanted steel granules that stick to them during the printing process, and these affect the surface roughness and dimensional accuracy of the parts to some degree. The surface also may contain cracks, which can decrease the strength of the part. So we used chem polishing to remove these. We did SEM imagery taken before we did any of the processing. And then we used a chem polish procedure developed at UDC to remove this unwanted material and cracks. And then we compared the surface roughness before and after the chem polish. So you can see on the platen there is our part in the SEM. And this is a 205 times magnification of the part. So you can see a large number of granules all over the surface of the compressive test part that we have here. And zooming in a little bit more at about 1,000 times magnification, You can see we have a lot of particulate between about 5 and 30 microns in diameter, and this was pretty uniform over the entire surface of the part. So this chem polishing procedure is using an acid bath to remove these particulates. And so the preliminary chem polish shows a massive improvement in surface finish. We had a huge reduction in particles, almost none that we could see in the 5 to 30 micron range, and fewer surface cracks. And we would expect that we could see a measurable increase in yield stress. This is something that we didn't have an opportunity to test. But you can see to the right there is a chem polished sample at 1,000 times magnification. And taking that, we can look at it 2,000 and 10,000 times on the left and right respectively. And you can see the surface is incredibly uniform and smooth. We don't have any of this particulate that we saw in the pre-polished samples. So from there, we were taking our data to design and print our steering knuckles. So they've been printed, not yet tested. In fact, they're still on the build plate exactly as they look right now. We used a relatively dense lattice structure at 45% relative density, so kind of cutting the middle between two upper ends. We had a really large reduction in mass compared to our previous Rover's steering knuckle design. So at 380 grams, we had a 90% reduction in weight. And we still need to remove these from the build plate, conduct milling to clean the face of the part, and then chem polishing to remove the metal particulate, particularly in the lattice structure itself. So we found that our prints are very close to the expected density according to the manufacturer's specifications. So a little more than 99% solid, which is pretty good for a powder bed printer. Our bending test showed that our samples were fracturing before the expected for relative densities. So that is a bit of a concern as far as that property. Our compression tests were a bit inconclusive, especially since the 40 and 50% relative density tests seemed to be flipped from what you'd expect. So that may be an artifact of using the brush blade during printing or some other flaw in the print. And the chem polishing procedure was very successful in removing particulate and surface cracks from the samples. So we had a huge reduction in that surface particulate. So for our future work, due to the stay-at-home orders, we weren't able to complete the Rover. As you can see in that picture, it's quite unfinished, and the upholstery looks terrible. So we would have liked to complete some more work. The tensile stress test articles, as we mentioned previously, our first set of tensile specimens didn't complete properly. We ran out of powder actually during the print, so we printed a new batch, which needed to be tested still. We need to do part integration of the steering knuckle and road testing. We would also like to do additional SEM work and chem polish testing, so testing the samples that have been chem polished versus the ones that have. And we also have some other kind of further along the line, characterizing the heat effects of the printing, heat effect simulation, and materialized magics. So that's the software we use to actually make these prints slice for the printer. You can see in that picture to the right, there's some bluish discoloration at the top of the part, and that's due to the uneven heating during printing. We also didn't conduct any heat treating of the parts, so there's still a large amount of internal stress in the parts, which could also contribute to premature bending and cracking. And we didn't conduct the martensitic aging process, so that would actually almost double the strength of our parts. And finally, more thorough surface characterization with Keyence optical microscope, which the school just got. And that would allow us to really make good comparisons of the surface roughness between the polished and unpolished parts. So here are a few of our primary references. We drew heavily on these in the literature review and characterization of our lattice structures initially. And finally, we would also like to thank our advisor, Dr. Xu, Tekele, our TA in the capstone course. We were supported by the CamStar grant here at UDC, and we were helped along by Dr. Klein, Dr. Tyagi, Mr. Pablo Sanchez, Josh Dillard actually was responsible for doing our chem polishing, and we are also Rover is funded and powered by the DC Space Grant Consortium. All right, that's it.
All right, very good. So yes, so now we can start the question session. So I already see some questions here. So this question is from an advisory board member. So he was trying to ask, have you tried to validate your simulation results against the results you found in the literature?
So we weren't able to get Lattice simulation results. We found that our actual mechanical testing was in line with our literature, but we worked tirelessly for several months using different programs to try to do the Lattice simulation, and we were unable to be successful.
Okay. Yeah. So it has been a very challenging task. There's a group, and NASA is also working on similar task, and they have been having some difficulty simulating the lattice structure as well. So there is another question: how did you get the actual density measurement for your sample?
So we used the manufacturer specifications and extrapolated what the weight of a solid would be for the geometry that we printed, and we did a comparison based on that.
Yeah, just to expand on that, we used Creo to do the mass and volume analysis. So we got the theoretical maximums from there, and then we're able to compare that.
Okay. Any question from the audience? There's one more question from Dr. Klein that are there other mechanical tests you would like to perform?
Well, I guess, yeah, the tensile tests would have been a really nice component to have added. And yeah, I think doing some more compressive testing with a different platen. I actually designed a adapter to go onto the machine to give us a flatter platen, which I think would have been yeah, more useful. Yeah, and fatigue testing as well. I believe we're in the process of getting a fatigue tester, so that would definitely be very helpful, I think, long term to see how these parts hold up.
Okay. I see another question. What effect of improving surface roughness may occur on the mechanical, especially the fatigue testing? You can check the.
Sure, and I'll actually kind of pull up the slide here on this part before post-processing. I think the biggest result would be the removal of surface cracks and these stress concentrations. Everywhere these little granules are touching, they're forming an incredibly small radius of curvature where they're touching, so you have more likely propagation of cracks through the surface. So hypothetically, a chem polished sample that's perfectly smooth, you're going to remove those failure points.
Right, which would be especially critical for these lattice structures where any cracks can propagate very quickly.
And I guess for the just general question for this lattice structure, you did mention a few applications. So where did you see this can be applied for broader context, like a different aspect, maybe not just for NASA, but for some other areas? Where did you see this can be applied?
I know there's some applications in biomedical field because you can create kind of artificial bone analogs with some of these structures. If you're doing a bone replacement or something along those lines, I know that that's one area of interest outside of the aerospace industry.
Okay. I guess maybe this is the last question. What's the most challenging aspect of your project? Or what's your experience with it? Maybe each one of you can share a little bit.
Okay, I guess I'll start it off, pass it to James and Waleed if we want to do it in that order.
Sure.
So I think we, at least from my end, I think we had some significant time constraints in terms of getting the printer up and running. So I was initially there for the printer training, and then our machine needed servicing, which gave us downtime, and then we had to go back and do it. So it was a lot of, I think that time crunch was very difficult in terms of getting the parts printed, processed, and tested. It was very short turnaround time. So from my end, I think that was probably one of the hardest parts.
Okay.
Yeah, I think the time constraints definitely. I mean, if we had another 6 months to a year to work on this project, we could do a lot of things with it. And for me, especially, it was going to be working on the simulation results. I tried several different programs. I tried to cheat the system in any way I could in order to get the lattice structure in there to be able to mesh it, but I just wasn't unable to do it.
And I will also touch on that as well with my teammates. Time for this project is an important aspect, especially like for mechanical testing. We'll gather more information on mechanical testing to provide for our rover design.
Yeah, I just want to mention that advanced manufacturing is a very critical part of our curriculum. And so, as you see, we have the 4 ME capstone project, we have tried to infuse the advanced manufacturing into those projects. So students can have experience on that. And also with the Metal 3 printer we have on campus, to really have the students have the opportunity to learn this very advanced technique and also get trained as an undergraduate student. It's very precious experience for them. So and so Dr. Thompson is here. So so I want to hand it over to her to introduce the BME group. So basically, this concludes all the ME capstone presentation. And thank you everyone for your feedback. If you haven't done the evaluation form, please don't forget to fill that out using the link in the chat box and select the right project if you can.